Okay, 12 o'clock, so we're going to have the last talk of the morning. So we have our own organizer, Manita, so from the Leibniz Institute for Baltic Sea Research. So she's going to talk to us a little bit about balance.
Right, good morning. Nice to present here and nice to be here, and also that all of you are present here for this workshop. So I'm going to talk about the balance conundrum, and you've heard this word around in the last talks, in the last days, especially in the lecture by Carsten, by Julian, by Alexa now, also in terms of mesoscale eddies, in terms of the ED, the baroclinic instability. And you've also heard a lot about waves itself, what they do, how they transfer energy, the break into turbulence, the triad interactions, and so on. So if you heard actually a bit about both the balanced part and what I like to call the unbalanced part, because to talk about the balance is incomplete without talking about the unbalanced motions. So essentially what I'm going to talk about is both the balance and the unbalanced motions and how they come together into addressing this balance conundrum. And of course, this work is done with a lot of different co-authors, but I'm not writing here. For example, Carsten, Dirk Olbers, Pablo here, and my PhD students who are not here, for example, Silvano and other mathematicians like Tuba Masur and Marcel Oliver back in Germany. Right, so the balance conundrum is actually not a new problem. It's a problem that dates back to more than a century old. This picture you see here is an artist's impression of the Richardson forecast factory. This was a dream of Louis Farrar Richardson, who attempted the first ever weather forecast during the First World War. And guess what? The forecast failed terribly. Can anybody tell me why? Yeah, well, the main reason was that the separation of the balanced and the unbalanced motions was not taken into account. So the unbalanced motions or internal gravity waves in the atmosphere and ocean can interact nonlinearly with the balanced motions or mesoscale eddies and kind of contaminate the signal, or as the flow evolves, it can diverge from the original, the balance equation that you have. So this gives you an impression of the scale of the problem, and even today, after more than a century later, with a lot of progress over decades, we have still not gotten very far with addressing this, but I'm going to show you recent progress in addressing nonlinear flow decomposition and how we can use it to understand more about atmosphere and ocean, but mostly with giving examples of the ocean. So another way of understanding this is what I like to call as game of notes. This is a musical analogy to these motions. So in 1947, Jules Charney was also known for the Charney type of instability. But this Jules Charney actually led to one of the first successful numerical weather prediction using actual computers. So actually what I forgot to show here is this was a dream of Richardson. So this is supposed to be Richardson in the middle, directing across the globe for simultaneous solving the Navier-Stokes equation for weather prediction with what he thought of human computers, because there were no digital computers by that time. But then Jules Charney in 1950, using the ENIAC computer, actually gave the first weather numerical prediction, and Philip Thomson was part of this team. So he wrote in a letter that we might say that the atmosphere is a musical instrument on which we can play a range of many tunes. So what it meant to say was that the low notes refer to the slow rotational motions or balanced motions, and the high notes refer to high frequency internal gravity wave motions. Also, the bulk of the energy is contained in the slow rotational motions, and although there is energy in the high frequency components, it's usually small, referring to inertial gravity waves or internal gravity waves, which are usually small in amplitude, but they do matter because they interact nonlinearly and affect the flow as it evolves. So Daly then further extended Charney's analogy to say that we can think of inertial gravity waves as meteorological noise that is not loud enough to drown out the symphony orchestra, though it does detract from the performance. So in the atmosphere, this noise is an inconvenience. In numerical models, it can be disastrous. So what it means is that if you look from the point of view of numerical weather prediction, where you actually want balanced state, which actually determines most of the dynamics of the atmosphere, when the presence of, inertial gravity waves actually leads to divergences from this flow, and it's an inconvenience when you want to predict this flow because you have to constantly deal with these noise. And of course, it's the same with the models if you want to use the models for prediction. But as they say, one person's noise is other person's music. So if you don't like internal gravity waves, you will call it noise. But if you actually want to chase waves, you want to use the same techniques to actually diagnose waves. So what I'm going to show is actually a bit of both, is how to diagnose balance, but also how to extract inertial gravity waves using similar techniques using flow decomposition. Right. So giving examples of the ocean, you have seen actually enough pictures in Julian's talk, Carson's talks, and Alexa's talk, what these motions look like, but I would still like to give an impression of how different these motions can actually be. So this is just impression from the ocean. So here you have a satellite image in the South Atlantic Ocean. So the colors are just from the phytoplankton bloom. So you actually see these large eddies of different sizes. And just for the scale, 1 centimeter here is about 100 kilometers. So they're really, really large eddies. And you can call them slow balanced motions. In the literature, you'll find a lot of different terms. Sometimes you call it vortex mode or slow mode, or Rossby mode. There was a term coined earlier, or slow manifold. I will talk a bit about this later. And then you have internal waves. So what you see here is this is near Italy in the Sicily Channel. You have these tidal motions, these internal waves which show up on the surface. This is picked up by the satellite because they modify the surface currents. So this is what you can pick up from the infrared band. And then you can see these internal wave fields. And again, 1 centimeter here is about 5 kilometers. So that's like a drastic difference between these two motions. And not only do they are different in scales and look different, the dynamics that generate them are also very different. So these internal waves are usually referred to as high frequency unbalanced motions, wave mode, fast mode, or a fast manifold. Okay, so we've also heard about this. Actually, Alexa did a very good job of explaining the different regimes. And I'm going to focus on the Rossby number, although Alexa also mentioned the Richardson number, so you can use them in equivalent. But I'm going to talk about Rossby number because later I'm going to expand the equations in Rossby number. So Julian gave a different definition of the Rossby number, so you can just define it differently. But here, for the sake of this talk, I refer to as a ratio of flow frequency to the frequency of rotation. So that's different for the balanced motions and the unbalanced motions. And in the ocean, you can find also in the atmosphere a range of regimes. So you have very small Rossby numbers, which are, for example, in a weakly stratified regime called quasi-geostrophic regimes. And then you go to higher and higher Rossby numbers, you get to ageostrophic regimes, which are strongly stratified. The other interesting part with the Rossby number dependence is that if you're at a large Rossby number, okay, let's put them the small Rossby number. If you're at a small Rossby number, the time scales between these motions are well separated. So there's weak coupling between these motions. But if you go to higher and higher Rossby numbers, you actually get to regimes where their time scale separation become complex, or basically becoming more and more non-existent, which means the coupling is strong and the separation becomes a challenge. So what does this mean in terms of energy? So why are we even interested in separating these flows if it's so complicated and so tedious? So you have also seen this diagram before in different forms of energy, the energy compartments in the ocean and the transfers. So here is a schematic where you have on the x-axis increasing spatial scales towards this direction and increasing time scales downwards. So you have the energy, most of it entering at the mean circulation from winds and tides and solar heating and so on. That's where most of the energy enters. Right, and this energy of the mean circulation is then lost to the energy of mesoscale eddies by baroclinic instability primarily. Of course, there are other ways to do that too. The interesting thing is that the energy in this part from mesoscale eddies is known to transfer energy back to the large scales. This is known as upscale energy transfer or inverse energy cascade. On the other hand, we have internal gravity waves, which span a range of wave numbers and frequencies. So that's a spectrum of internal waves, which lose energy by wave breaking, by convection, or shear instabilities and other ways, to small-scale turbulence, where the energy finally dissipates. Also, this part of the compartment, energy compartments, is known to transfer energy towards small scales. This is called as downscale energy transfer or forward energy cascade. So what's missing in this picture is now a link between these large-scale reservoirs to these small-scale energy motions, where actually the energy finally dissipates. So here, of course, there are sub-mesoscale, which is also a candidate, but here I'm going to focus on internal gravity waves, which can form a link between the energy transfer from here to here. And this is, again, important for the energy dissipation and to understand how the energy ends up here. And there are a lot of different processes that have been put up in the literature in different regimes and different approaches. For example, light-held radiation, ageostrophic instabilities, and of course, spontaneous loss of balance. entry instabilities, which is what I'm going to talk about, and how which of these are more important in determining this process. What makes it interesting to look at this process of transfer from mesoscale entities to internal waves is, of course, first of all, eddy dissipation, eddy energy dissipation. But the other thing is from idealized models from atmosphere and ocean, the estimates of energy input into waves from this process are estimated to be about 0.3 terawatt. The striking thing about this number is that it's the same or similar order of magnitude as the energy input into waves from winds and tides, which is actually, yeah, quite striking and surprising. And it's important, therefore, to understand how important this process is and if it's actually really amounting to that much. I'm not going to give you the global estimates at the end, but I'm definitely going to tell you which one is important. But for that, it's important to deal with the flow decomposition that I will show later. So I want to address the balance conundrum topic using 3 different concepts. One is the swinging spring. Then I will talk about the slow manifold. And then I will talk about the spontaneous loss of balance itself. So I'd like to give this mechanistic example to show how the balanced and unbalanced motions are tied together. So what you have here is a system where you have a pendulum tied to a spring. This is at rest. And when you let the pendulum into motion, you have what you get here is low frequency motions, which is analogous to balanced motions of the ocean and atmosphere. What happens is, although your system was at rest in the beginning, the motion in the pendulum induces a motion in the spring, which is analogous to high frequency oscillations that you see in the atmosphere and ocean in terms of internal gravity. What it also means is that the balanced motion or these low frequency motions almost always induce motions almost always induce high frequency oscillations, which means balanced motions always generate unbalanced motions or internal gravity waves. This is actually also related to this scale separation issue, or just the scales. You can assume geophysical flows to be of 2 time scales, a slow time scale and a fast time scale, which again depends on Rossby number. I will talk again about this later again. But this brings me to the concept of slow manifold. So the fact that you have a balanced motion which always generates unbalanced motions, it means it always diverges from its state of balance, which means that so a slow manifold would mean if you're in a state of balance, you always remain in a state of balance. But the fact that it's not always the case, it means you don't actually have a slow manifold, but rather a fuzzy manifold. And just to give you an impression of how confusing and challenging this topic has been over decades, I just want to show you a bunch of papers that you can actually find in this book on numerical weather prediction. Actually very interesting. So it started back in 1986 by Lawrence on a paper on the existence of slow manifold, and just a year later on the non-existence of slow manifold, and just a couple of years later again on the existence of a slow manifold with some system of equations. And it's getting just to a totally different regime on the slow manifold. What is it? So you see the confusion has lasted, not just, it hasn't actually stopped. There are a bunch of papers after that too, and we're still working on it, and it's still a question to answer, both mathematically and physically. So the answer to this question is actually, this is not the question you should be asking, if there is a slow manifold or not. You should be asking if there's a strict slow manifold or not, which means that if you're on a slow manifold, will you always remain on a slow manifold, or do you diverge? So it's clear that you always generate internal gravity waves, but how invariant your slow manifold is. So I will also show a bit of that later, but before that, I want to show you how to do flow decomposition, and before that I want to show you what it looks like in a model simulation. So this is a balanced jet, right? This is geostrophically balanced. There is no wave in the beginning. And if I just let it run, you will see that slowly this jet meanders. It meanders, then it generates these eddies which pinch off from this meander. And after some time, along the edges of these eddies, you also see these finer, smoother features, which are actually unbalanced motions.
The plotting?
Pardon me?
What variable is plotted?
This is just horizontal velocity. Right, so you see these abundance of small-scale features that show here, and then you actually see that a balanced field generates unbalanced motions, and at the end, when the flow evolves, you actually have balanced and unbalanced motions coexisting, which makes it challenging now to separate them. So now I'm going to show you that these unbalanced motions are prevalent both in atmosphere and ocean, but just because it's waves, is it really wave? So these are just some examples of diagnosing waves in different ways. So this is an example from atmospheric. This is a classical paper in atmospheric science. So this is shown on below is the horizontal velocity divergence. Sorry, it's on the top. Below is the pressure field in the upper troposphere. And here on the top is the horizontal velocity divergence, which is often used as a signal for waves. So here you see the troughs of these pressure contours, where you also find the packets of internal gravity waves. This is sometimes called pancake-like structures. So you see that they coincide with where the pressure contours are. Then this is an example from the ocean model. So again, you have here the pressure contours in the Gulf Stream region, which is supposed to be full of eddies, and the colors indicate the high pass filtered vertical velocity. So this is supposed to indicate the existence of waves. And again, this is just vertical velocity from a model of baroclinic instability, and you again see these the red and the blue alternating patterns, which is an indication of a clear wave train. But the question is, just because it looks like waves, are they really waves, or they're just apparent wave signals or slave modes? Because here, there is no diagnostic or no dynamic flow decomposition taken into account. It's just divergence and vertical velocity. So to look at that, we actually need to do what we call nonlinear model decomposition. So I'm going to show you a simple example using a single layer model, shallow water equations, although this has been done for primitive equations for hydrostatic, non-hydrostatic, and a bunch of different configurations. It works in every regime, just your equations change a bit. But just to illustrate the concept, so we start, for example, with a single layer model here. This is the equation for horizontal velocity, and here is the equation for the height field. Rho is the Rossby number, and in the Fourier space, you can write your equations in a way that you can collect your linear terms in this matrix A and nonlinear terms in this vector N. The Rossby number here shows up with a nonlinear vector, which means that it determines the nonlinearity in the system. Right, so this is your matrix A. This is your vector Z, which just consists of U, V, and H for this system of equations. So this is your matrix A. So from this matrix A, you can actually calculate eigenvalues and eigenvectors. So you get 3 eigenvalues, one which is related to 0, which is related to the balance mode or the eddy field, and then the other 2 which are related to the unbalanced mode. If you notice carefully, you will also see that this unbalanced mode eigenvectors, eigenvalues also resemble the dispersion relation for gravity waves. Right, so from this you can construct left and right eigenvectors here for both of these eigenvalues, and then you can actually use them to create projection metrics that you can actually project back to the state vector. So this is what's happening here. So this is just a projection matrix P. S is the subscript for the balanced and the unbalanced mode, and you project it back to the state. So at this point, you actually have separated your balanced and unbalanced motions, and you can invert it back to the physical space, and you have the separated motions. You can simplify this problem if you don't want to take into account the nonlinear part. You can just ignore it, and you have the linear decomposition. But if you include it, then you have the nonlinear decomposition. Okay, now this was where we do the eigenvalues part. But now we actually go to higher orders. We expand our equations in Rossby. So this projection that I just showed here, if you just put this back in your original system of equations, you actually get something like that. You have the Rossby number here with the projection matrix here. And then if you just write it down something like this, you get something like I, which is the interaction coefficient, which actually combines all these different separated modes that you got. But what's more important here for this high order decomposition is, because you're expanding in Rossby number, is the time scale separation. So there are a couple of assumptions here that we use. First is to introduce these 2 time scales that I talked about earlier, fast and slow time scale. And the expansion is done, for example, using this classical paper from Wang. But the slow mode then evolves only with the slow time scale. So that's the G0 with a capital T, which is a slow time scale. But when you have your unbalanced motion, it actually evolves with 2 time scales. There's a slow and a fast time scale. And this is because we have what the so-called slave modes, which are not waves, but they show up with the waves, but they're actually some related to the balanced motion. That's the part that evolves with the slow time scale in the unbalanced part. So this is how you can actually expand your equations. I'm not going into the details, but just showing you how it works in principle. So you can expand these equations in Rossby number. You just go to higher and higher orders. And with every order for the fast modes, you actually eliminate the slave mode. So the F part is just the slave modes, and you suppress any of these wave generation by going to higher and higher orders, which means that if you go to higher orders, you're suppressing more and more wave generation, and you have you're getting closer and closer to a more invariant balance state. So actually, if you go to higher order, the higher order you go, the balance state is free of the wave field. At the same time, if you go to higher orders, you have a more accurate description of what your wave field is. So in fact, what you're doing is for the wave field, you're just removing the slave modes for each subsequent iteration. I just wanted to point out here that if you stop at the first order, what you get is the quasi-geostrophic balance state, which is also used in some of these other numerical prediction papers. But in fact, it consists of a lot of slave modes and hardly any wave mode, which I will also show later with contour plots. So it's another animation. I just wanted to show how the equations turn into reality or modeled reality. So here you have the full state, which consists of the wave field and the balance field. And this is what you get when the separation. So you have here the slow field. You can see it's a nice separation, and here is only the fast mode. This is what you get with the nonlinear flow decomposition. So I will play it again. And I just wanted to emphasize that because it's a nonlinear problem with nonlinear interactions, if you just do linear decomposition, you will not be able.
It looks like you have these strong gradients moving. Are those shocks?
Oh, where?
Are those shocks? When you play that movie, can you play that again? It looks like you have these very strong gradients, which looks like shocks.
You mean here?
In the red region, there are these traveling strong gradients.
Oh, you mean here?
Yes.
This is because it's superimposed like that. This is a particular example to show the separations. It's superimposed with the wave field in the beginning to show that the decomposition.
But it looks like they're shock waves that form.
Okay.
Are they? Have you looked at it? Is it
no,
shock wave?
We haven't. But maybe we can talk about it later. The fruit number, I also haven't checked that. But this is like Rossby number 0.5 or so. I haven't checked the fruit number, corresponding fruit number. All right, I think I don't have a lot of time, so I will skip some details. But what I want to show you is maybe I just skip that. I just want to show you an example of diagnosing waves in non-hydrostatic simulation. So what you have in the beginning is a jet-like flow, which is balanced. But here I want to look at both spontaneous loss of balance and shear instabilities. So here there's lateral and vertical shear superimposed on a balance field. And then what we do is stability analysis. And then from that, you can obtain eigenvalues for different Rossby numbers. I'm just showing one example of Rossby number 0.3. But what you can see is for the eigenvalue, which is 0, this is corresponding to the geostrophic unstable mode or the flow or a field where you actually don't, it's like the balance field or geostrophically balanced field. But actually, if you take a positive or negative eigenvalues, which is corresponding to positive or negative frequencies, you actually get to other modes, which I am calling here a geostrophic unstable mode. And this would be an example of a sheared flow, a balanced shear flow. So what we do is after this, you actually initialize your flow with each of these eigenvectors, but then you balance it with this higher order balance up to second order in Rossby number. And then you can diagnose the internal wave emission for these two different cases. But here you have balanced your flow, so you actually have no waves at this point. I just wanted to show that for different Rossby numbers, for one particular Rossby number for given conditions, you actually satisfy the condition of symmetric instability. So this is just a normalized potential vorticity, which gets inverted here, and that's the condition of symmetric instability. So that would be the case for sheared flow, and I just wanted to quickly show what it looks like for different orders. So here you have different Rossby numbers, and the first order on the top. So on the top you have just the vertical velocity, and below you have the balanced first order balanced velocity. What you see on the top is actually there's no difference between the top and the bottom, which means that the top part is actually dominated by slave modes. So you have to go to higher orders to be able to detect some waves. So you actually see if you go to higher orders and large Rossby number, you actually begin to see some differences, which is actually waves. And before that, it's all slave modes, which means that the spontaneous emission, as was classically thought, is actually not that strong. It's dominated by slave modes, and it's rather weak. But if you look at the case with the shear flow, you can actually see that already in the first order, where you have vertical velocities, you begin to see differences. You begin to see differences already at the first order and also for smaller Rossby numbers, which means that when you have shear imposed on your balance field or shear instabilities in the balance flow, it's actually more prominent in generating waves, and you can also already detect them at lower orders. Yeah, that's just showing what the Rossby scaling looks like for this wave emission. for higher orders and for different Rossby numbers. So the higher and higher order you go, the more wave emission you can detect, but this is mostly the case for larger Rossby numbers. Now, what I wanted to show quickly was, this was higher order balance, but you may ask, if you have a different balance scheme and you give me a different balance, is it the same balance? Or is it a different physical balance? So what we did was we compared the higher order balance to a different concept of balance, which is called optimal balance. And this is a simplified schematic of what it looks like. I'm not going to go into detail, but just to show it's an iterative forward-backward scheme. So you actually start, maybe I showed this animation to explain you better how this works. So on the x-axis, actually, you have what you would have a perfect slow manifold. This is the balanced part. On the y-axis, you have the unbalanced part of the wave part. So whenever your flow is in between here, this blue curve is actually when you have wave emission. Well, what you try to do is every time you go to a perfect balanced state, but your flow diverges from it. I will play it again. So you go here. This is where you put your flow to. Then it diverges again, and you force it to go to the balanced state again, and it diverges again. But so it changes the nonlinearity here. But what happens is, after a certain number of iterations, you actually get back to a closer and closer to the actual balance state, and that's the concept of optimal balance. And we try to compare these both methods, and the good news is actually when you compare them, so this is the comparison here, the blue and the yellow and the red curve, you see that they're quite comparable here on the scaling, which means that the balance state that you get from both of them are quite similar. And I'll just quickly show what it means in terms of diagnosed imbalance. So this is, we start both the methods in the exactly similar model setting and diagnose the imbalance in two different cases. One is the jet-like flow in a random field. Then we balance it and we diagnose the imbalance at the end. And you see that these is several orders of magnitude smaller, meaning that you have very, very small wave emission. And although you don't have a perfect balance state, what you can get is a nearly invariant balance state or nearly invariant slow manifold. I think I have maybe just 2 minutes to finish. So this is just a summary of the methods that I showed, because I said I will just summarize the recent developments in it. This is higher order balance, this is optimal balance, and just a teaser of a very new method that we have developed, which is called optimal balance with time averaging. The cool thing about this new method is that you can actually go beyond the scope of these two methods, which are limited to idealized settings, because you cannot because you cannot apply Fourier transform to a situation with boundaries and with beta plane, etc. But with this new method, we can do that. But I'm not going to talk about detail here. But what I want to talk about is now the fact that you have separated your eddies and internal gravity waves. What can you do with it, right? So I think we will have further talks about different interactions and scattering, etc. I think Zoe talked a bit about it, and we had a talk from Mani about the interactions and so on. But that's what I mean. If you don't, so for now we were generating waves from eddies when there were no waves in the beginning. But if you have both of them, you can have a bunch of interactions. And what you can do is, so this question of energy transfers, what happens with energy transfers and in which direction it occurs and which processes determine it. This is what you can infer, at least to some extent, using these decomposition. So in the picture earlier, I showed that the balanced motions show a dominant upscale energy transfer. But what I'm going to show here is that the balanced eddies can also have downscale energy transfer, and this is what you can get here. So what I'm showing here is using these decomposed velocities to infer small-scale and large-scale dissipation from the kinetic energy equation. So the hatched part shows the small-scale dissipation, and the black part shows the large-scale dissipation. And the striking part is, for all Rossby numbers, you have a downscale energy transfer from the balanced motions, even for a really small Rossby number. So some processes are already showed here, but it also has other implications, for example, for energy budget, eddy parametrizations, such as backscatter and eddy wave interactions and so on. Also for mixed Rossby gravity wave interaction and so on, which we explored in a different way. And of course, Pablo will talk about eddy wave interactions from this model that was recently published in a JPO paper. And then I talked about downscale energy transfer from unbalanced part. What I want to show you here, again, from a similar calculation of dissipation terms, that the waves can also transfer energy upscale. But it's not so clear what processes are responsible for this. It has implications, again, for energy budget and wave wave mixing parametrizations like EDMX, which actually doesn't include these processes anymore as of yet. But some processes that might be responsible for this upscale energy transfer could be wave-wave interactions, eddy-wave interactions, not only by resonant, but also by non-resonant interactions, which we have explored in this paper. And I'm in my summary. So actually, I told you about balance conundrum using slow manifold, the swinging spring, and the spontaneous loss of balance, and how spontaneous loss of balance is actually rather weak as compared to shear instabilities. For example, this particular case of symmetric instability using nonlinear flow decomposition. This brings new insights into geophysical flows, and it's a striking result to understand how spontaneous loss of balance works with atmospheric and ocean dynamics. Of course, the conundrum doesn't end here. There are more conundrums to solve. For example, what happens to balance at boundaries with Kelvin wave generation, and what happens at equator. This is not, it's not so easy to answer these questions yet, but hope we can answer in the future. The take-home message of this whole talk is that the balance conundrum is here to stay.
Yeah, thanks for the talk. Are there any quick questions before we close the session? Jim?
Yeah, I thought earlier you said spontaneous generation across the whole globe was like 0.3 terawatt or something. Now are you saying they're weak?
Yeah, because that's from the idealized models, estimates, and they're not based on nonlinear flow decomposition. They're based on Helmholtz decomposition. That's the question.
So what is the answer? What is the spontaneous emission across the whole globe?
That's difficult to answer because it's difficult to diagnose it in a global setting using nonlinear flow decomposition. So hopefully with this new method, because you have boundaries, you have topography, then you have changing beta and at equator. If you want to do it globally, it's not so simple. So that was the point of this estimate that was there before. It's kind of a bit far-fetched because it's not accurate and it's not so reliable. Because at least we see here in multiple methods and different configurations, it's consistent that spontaneous loss of balance is weak. But to give a global estimate is kind of, if you don't want to do it precisely, it's kind of difficult. But hopefully we can do this with this new method, but there's still some challenges to overcome.
And is this method, the decomposition, does it give you orthogonal fields or is it not orthogonal?
It would give you the same fields that you would get from optimal balance, for example. The same balance in the unbalanced field. It's just a different concept. So it works, it has the same level of accuracy as the other method. It's just.
But the question is, are the fields orthogonal in a sense, and can you write?
Yeah, that's what we assume.
Can you write the energy as balance plus unbalance without any cross terms?
Yeah, that's what we do usually in these methods. That's what you can do. Yeah. The question.
One question online. Do you mind reading it out as well?
Okay. The question is: in the jet simulation, are we taking into account the fact that the jet propagation produces a shock in the medium, which might trigger more eddies through turbulent vorticity generation? Yeah, that's a good question, and yeah, it's definitely a possibility. So I haven't addressed it in detail, but what I showed here are rather idealized simulations, and we also don't always run them long enough to probably generate more motions. But you're right, you can generate eddies, waves, and lots of other fields. And some of the processes that I mentioned, you have eddy wave interactions, wave interactions, and a lot of these bunch of energy transfers. It just gets a lot more complicated, so it's difficult to diagnose that. It would be a thing to do in the future to do it more efficiently, but it's not so straightforward to do. So that's why, for the sake of the talk that I showed and the simulations I showed and the separation, we just kind of start with a balanced flow, and at the end of the flow, we just diagnose the imbalance. But you're right, there could be a lot of other processes when the eddies are generated, and they might trigger a lot of different motions on the way. But it's difficult to diagnose.
I think for time reasons, we should probably close the session. So if you have further questions, then feel free to find Manita over the lunch break. So let's thank Manita again.
Thank you.